Suppose I have a finite dimensional vector space V, and F is in L of V. That is, it's a linear transformation from V to itself. It's important that it's the same V on both sides here. This wouldn't be true if I had written LVW. Then the following are equivalent. A, F is invertible. And remember that an invertible linear map is both injective and surjective. B, F is injective. And C, F is surjective. And so the content of this is, we already know that invertible is the same as these two, but the content of this is that in the case that F maps V to itself, it's enough for it to be injective. That implies surjective, which we proved last time. If it's surjective, that implies injective, and those two together imply that it's invertible. So suppose we did the other direction last time. Suppose that C holds, F is surjective. In that case, the range of F, so F goes from V to V. If it's surjective, then the range of F is just, we want to show that it's equal to, or it's equal to V. The range of F is V. And the dimension of V is the dimension of the range of F. So the rank nullity theorem tells us that the dimension of the null space of F is equal to the dimension of V minus the dimension of the range of F. But V and the range of F are the same thing. Their dimensions are equal. So that's equal to 0. The only vector space, which is dimension 0, is the 0 vector space. All F is the 0 vector space, and so F is injective. And since it's both injective and surjective, it's invertible. So recall that we said that two vector spaces, V and W, over a field F are called isomorphic if there exists an invertible linear transformation F from V to W, and so there's an inverse, F inverse, that goes back in the other direction. Now it's a favorite activity of mathematicians to define a class of objects like vector spaces, define a notion of sameness, say that two vector spaces or two of whatever objects are isomorphic, and then try to classify all the objects up to isomorphism. Sometimes that's very hard. Sometimes it's somewhere in between, like if you've seen theorems about groups, abelian groups, simple. And sometimes it's very easy. So in this case, it's very easy to characterize when two finite dimensional vector spaces are isomorphic. Two finite dimensional vector spaces are isomorphic if and only if they have the same dimension. if they're isomorphic, they have the same dimension. If they have the same dimension, then they're isomorphic. So it's important, and I'll keep repeating, that just because they're isomorphic doesn't mean that there exists a particularly nice or natural isomorphism. So they might be isomorphic, but there might be many different choices of isomorphic. For example, the blackboard extended infinitely the two-dimensional vector space. This table is a two-dimensional, extended infinitely the two-dimensional vector space. But if I asked you to map one to the other in a linear way, you might choose different maps. Okay. So let's prove this. First, suppose we have an isomorphism. Suppose F is an isomorphism. And by the rank nullity theorem, I can write the dimension of V. So there's an isomorphism between two vector spaces, V and W. I can write the dimension of V by rank nullity is equal to the dimension of the null of F plus the dimension of the range of F. So now isomorphism is injective and surjective. So the range of F is equal to W. The null of F is equal to the 0 space, and the dimension is equal to 0. So we're saying the dimension of V equals 0 plus the dimension of W. So the dimension of V equals the dimension of W. On the other hand, assume that V and W are finite dimensional, and the dimension of V equals the dimension of W equals some positive integer n. The dimension is the length of any basis, so let's take a basis. Of each space. They both have the same length since the two spaces have the same dimension. And then we can define the most obvious map. Notice that I had to pick a basis in order to define this map. I can tell you a linear map by telling you where it sends each element of a basis. So I'm going to send Vi to Wi. And you can check that that's an isomorphism, but I hope it's clear. Right? What would its matrix be? V1 up to V and W1 up to Wn. Its matrix is just going to be the identity matrix, all ones along the diagonal and zeros everywhere else. And you can check that that's injective and surjective, or that it's invertible. So again, two things can be isomorphic without being naturally isomorphic, without everyone agreeing on what isomorphism we should use. In this case, that corresponds to a choice of basis. Yeah.
Does the dimension of null of F always equal 0?
It does if F is injective. We assume that F was an isomorphism. In particular, it's an invertible map between vector spaces, and so it must be injective, because otherwise it would destroy information. It would send 2 points to the same point, or a point to 0, and there'd be no way to invert it to get that pre-image back out. So it's not always true, but it's certainly true for isomorphisms. So I'll talk a little bit about this map that associates to a linear transformation a matrix after a choice of basis. It's a little bit confusing, so we've already talked about it once, but I want to say a few more words about it. So let's take an example. Suppose I have a vector space which is arrows on the blackboard, and I'm interested with some common origin, and I'm interested in the map reflection through this line. So this vector gets sent to this vector gets sent to that vector, and so on, reflecting through the line. And then I can associate to that. So that's a linear map. You can check that it's a linear map without choosing a basis, right? I can say something like, well, if I start with this vector and I scale it by 1.5, and then I reflect it, I get the same answer as if I reflect it and then I scale it. So that tells me that it commutes with scalar multiplication. Or if I take this two vectors and I add them, it doesn't matter whether I add them first and then reflect, or reflect and then add. Right? So it tells me that this is a linear transformation because it respects addition and it respects scalar multiplication. Now, what matrix is associated to it, of course, depends on the choice of basis that I make for the blackboard. There's a nice choice of basis, and I could pick, say, two perpendicular vectors like that. This vector here, when reflected through the line, just gets sent to itself. This is called u1, and this vector gets sent to its negative. Right, so on that basis, so here our vector space, our domain and our codomain are the same vector space. So this is just as the case of an MBB of F. The basis is the same for both the vector space and the domain and the codomain. So u1 gets sent to u1. So I put a 1 there. I put zeros here because there's no component of u1 in the image of u2, and vice versa. And u2 gets sent to negative u2. So that would be its basis. On the other hand, I could have made a different choice. For example, I could have chosen this vector and that vector as a basis. So u1 and, or let's call it v1 and v2 on either side of the line. And in that case, well, by reflection, v1 would have gotten sent to v2 and vice versa. So that matrix would be v1, v2, v1, v2 would look like that. Perpendicular. And if I made different choices, I would get a different matrix. The point is that we had a theorem last time, which I'll state again in another way in a moment, that said that this map from linear, in this case, linear transformations from a vector space to itself, of which this reflection is an example, to matrices, in this case, 2 by 2 matrices over, say, C. Matrices 2 to C, which depends on a basis. We argued that this is linear, but it's in fact invertible, and this is in fact an isomorphism, but it's not in any sense canonical because the basis that I choose determines which matrix gets associated to an F. There's no particular matrix. Okay, so let's make that a little bit. Let's say this invertibility thing as a proposition. So let V and W be finite dimensional vector spaces with bases B, V1 up to Vn, and C, W1 up to Wm, respectively. Then this map assign a matrix which goes from the space of linear transformations from V to W to the space of matrices. Now these matrices are going to be m by n, m rows and n columns, because the input space has n vectors. The input space is spanned by v1 up to vn, and the output space has m vectors spanned by w1 up to wm. This map is invertible. And so these L, V, W, and Mat, M and F are isomorphic vector spaces. But they're not isomorphic in only one way, they're isomorphic in many different ways, depending on how we select our bases. So let's at least sketch out a proof of this. Well, first we might like to show that it's injective. That is, we're interested in the null space, the set of linear transformations F, such that MBC F, such that MBC of F is equal to 0. And the set of all linear transformations which have as their image the 0 n by n matrix. That's the matrix n by m by n matrix of zeros. Well, excuse me. Suppose that we have some f which gets sent to 0 by this. And let's let vi be a basis element of a basis vector for v. One thing that you can convince yourself by a calculation, that I'll skip, is that MBC of FV equals MB of MBC of F MB of V. And more generally, that's true for linear, for if I want to compose two linear transformations. And so if this thing goes to 0, f of vi equals MBC of f MB of vi. Sorry, I should have an MBC over here. That's equal to 0. By linearity and thinking about what this definition of MBC is, we get that f must have been 0 if that's true for all basis vectors. In other words, it's going to show that f sends everything to 0. And so, in fact, the null space was equal to 0, and MBC is injective. On the other side, surjectivity for surjectivity, what we want to show that we can reach any matrix. So if I give you any m by n collection of field elements, there is some linear map that gives me that matrix. So suppose I have such a matrix, A11 up to A1n, AM1, AMN, m by n matrix, with each aij a field element. Let's define, and this is labeled, of course, by basis vectors of v and basis vectors of w. Let's define the linear map in the pre-image. I can define a linear map by telling you where it sends basis elements. So let us just send the kth basis element, so the kth column, which corresponds to the linear combination. The first column is A11 times W1 plus A21 times W2 and so on. Right? So we want this to get sent to sum from j equals 1 to m, aj k, wj. So this is the linear combination that represents that's given by the kth column of the matrix. And so if we make this choice, then MBC of F will be equal to the matrix we're after, the matrix A. So that has a nice consequence, which is that it tells us how to compute the dimension of a space of linear transformations. Right? It tells us that LVW is isomorphic by some choice of basis to the space of matrices with dim W rows, dim V columns over the field. In this, we had this be M and this be N. So those two things are isomorphic. And we know that from the previous theorem today that two vector space, finite dimensional vector spaces are isomorphic if and only if they have the same dimension and they're over the same field. These are isomorphic, so they have the same dimension. So that tells me that the dimension of L of VW equals whatever the dimension of this space is. But as a vector space, this is nothing special. This is just m times n elements of the field, right? It doesn't know that it's in a matrix form. It's just a list of elements. As a vector space, it knows nothing about the fact that it's a matrix. So the dimension is equal to m times n, or dim w times dim v. And if you want to give an explicit basis for that, of course, you can use just a matricized version of the usual standard basis. That is, you can use, say, if n equals 3 and m equals 4. So we have 4 by 3 matrices. We could have, say, use E, but it now has two indices. E2, 3 would be the matrix which has a 1 in the n equals in the second row in the third column, and a 0 everywhere else. Right? If I add together a scalar multiple of that plus every other possible combination, then I can write down any matrix. That's how we write down a matrix. So I exhibited a basis of size nm. So it's obvious that they're independent, and so that must be what the dimension is equal to. I want to give another example to illustrate this idea of whether an isomorphism is given, given to us or something we have to choose by thinking about this space here, V dual. So V is a finite dimensional vector space, and V dual is the space of linear transformations from V down to the field. So V has dimension n. What dimension does V dual have? Yeah. Well, okay, so I choose this matrix without any reference to a basis. And so, okay, right. So here's the order of operations. First, I choose the matrix A with no labels. Then I'm allowed to choose any basis I want for V and any basis I want for W.
So you choose the W first.
And I think of those basis elements as the labels in my matrix. In other words, we define the function this way. So first I choose the matrix, and then I could choose the basis after that. It doesn't.
Yeah, the way you set up is like you have to decide the basis for W first, and then get
Oh, this, you mean? No, I mean, no, because, so this is just saying whatever basis I have for V, whatever basis I have for W, I can define a linear map in terms of those two basis elements and the data of the matrix.
But if you already, like, if you choose the random basis first, then what if it doesn't satisfy the basis equation? Like the linear map, like F of V. So you should just decide the basis for W vector space first and then find the system.
Yeah, okay, so I guess what we're saying is, okay, fixing A in MBC, there exists an F such that MBC of F equals A. Does that make sense? Okay, thank you. Okay, so I was saying if dim V is equal to N, what is the dimension of V star, V dual? If you don't know the answer, you can try to think of a basis for it, right? So suppose V has basis, or I pick a basis V1 up to Vn for V. I can write an arbitrary element of V as the sum from I equals 1 up to n, say xi vi. And I can then think of these xi's. So something that eats an element of V and spits out an element of the field. This is a coordinate function. Right? The map that takes a vector and tells you its ith coefficient. That's a coordinate function, and that's in fact a linear map. And that, I would argue, defines this defines a basis for the space of linear transformations from V to the field. Right? Because I can write every such linear transformation as a linear combination of the entries in the vector. Right? So that means that the dimension of V star, now let's forget the basis. We just needed it to prove that, is equal to the dimension of V for V finite dimensional. And since they're two finite dimensional vector spaces that have the same dimension, they're isomorphic. Okay, so now forget the basis. I give you two vectors, uv and v. And I want to think of one of these things as v star. So I want to pick an isomorphism. That means there's some function, f, such that there is a, to each u I can associate a function fu that when I apply it to v gives me some field element. Okay? The point is that there's no canonical way to do that, actually. Without choosing, if I have a basis, all I can do, I can just take the transpose. But if I haven't chosen a basis, there's no way to assign such a function. We can all make a different choice. So it's true that the finite dimensional vector space and its dual space are isomorphic, but they're not naturally isomorphic. They're not canonically isomorphic. However, if we go one more, we can get a natural isomorphism. That is, consider now the space V star star. That's the space of linear transformations from V star to the field. That is, it eats an element, alpha, which is itself a function from the vector space to the field, and it spits out an element of the field. This also, by the same argument, right? I just added a star to both sides. This has to be isomorphic also to V and to V star star. But this guy is canonically isomorphic to V star star. V and V star star are naturally isomorphic or canonically isomorphic. That is, informally, there's a way there's a rule for assigning an element of this for every element of this that's linear. and that we would all come up with the same answer. We could all come up with the same answer. There's no choice that we have to make in order to find it. What's that rule? Well, okay, an element of this, that's a linear function from v star to f. So it has to eat a function from v to f, which is what this is. It has to eat that and spit out a field element. And it has to depend only on this. Okay, so we want to take an arbitrary vector v here and send it to something which eats an alpha, a function that, where alpha goes from v to f, and spit out a field element. And the only one that I can choose without making any further decisions is just to plug in v. So v was an element of the vector space, alpha can eat v, and that thing is a field element. So there's a lot of arrows here, but this is a way to define a canonical isomorphism. So the statement is that a finite dimensional vector space and its dual are isomorphic but not naturally isomorphic. However, a finite dimensional vector space and its double dual are naturally isomorphic by this plugging in map. We have a little bit of extra time before I get into polynomials, the beginning of polynomials. So let me just draw a couple of pictures about what this looks like. So we're saying that, remember, in our diagrams, the field is represented by the blackboard. And so this represents a vector, which is the same thing as a map from the field to the vector space. If I have two vectors, there's no way, canonical way, to from this create a map from the field to the field, which is the same thing as saying a field element. Multiplication by a field element is some map that goes from the blackboard to the blackboard. But there's no sort of obvious way to plug these together unless I had the arrows somehow going against each other, which is not allowed. However, if I have a vector and a element of the dual, that is a map from the vector space V to the field. So this thing is in alpha in L of VF. V is in L of FV, which is also called V. There is a way to plug these together without breaking any rules and without making any decisions. That's what we're saying.